Greetings. In this video, we'll be taking a look at something called dandelion spheres. Now, what are these spheres? And also, by the way, we are going to take a look at a theorem involving these dandelion spheres. So, let me first tell what a dandelion sphere is. Consider a cone. Just a moment. Yeah, consider a cone. Now you cut the cone into two pieces, not necessarily equal pieces or anything like that, any random two pieces. Now if you see, if you cut the cone in a slanting manner as shown in the figure, then it will create an elliptical cross section. So this is an ellipse, okay, and now you have two pieces of cone. One looks something like this, the other looks something like this, okay. So you have now two pieces of cone. Now you have to fit in a sphere. So consider this upper piece of cone, okay. Now the sphere should touch the two sides and also the plane of the base, okay. So you see, if the sphere is too small, it will just touch the two sides, and if it is too big, then it will touch the two sides all right, but it will not touch the base. But between this small and big spheres, there is a sphere which is of the exact size such that it just touches the three sides, that is to say the sides of the cone and the base, okay. Same goes to the lower piece of the cone. You have to have a sphere which just touches all the three sides, that is to say the sides of the cone and the elliptical cross section that the cutting has created. So these are the two spheres that you get, and this picture that is there on the screen is exactly that picture which I just described, and these two spheres are called dandelion spheres, okay. Now a theorem that we are going to discuss is the following: these two spheres touch the ellipse, the elliptical plane that you see over here, touch the elliptical plane E such that they uh, touch this plane at the focus of the ellipse. Or I can just say sphere touch the plane E at the focus of the ellipse, at the focus of the ellipse. So this is the theorem. So how do we prove that? First of all, we are going to consider the following. Uh, Consider an ellipse. I mean, before we discuss the proof, I just want to make a few things that we will be using here, okay. The first thing is that every ellipse has two foci, and if you have a random point P, then f1p plus f2p is equal to a constant. This is something that we are going to use. So if you see, if I mean, this is the corollary of this is something that we are going to use. Suppose you know that this is an ellipse, this is a point P is on an ellipse. Suppose this is something that we know, okay. Then if you take any two random points A and B such that AP plus BP is always a constant, then we can tell that A is the focus and B is also the other focus. So that this is one thing that we will be using in some manner, okay. And the other thing that we'll be using is the following. If you have a circle and a point outside the circle, you draw two tangents to the circle, then these two tangents are equal in length. Now we are going to extend this. We are going to say that this can be applied for a sphere as well. This can be applied for a sphere as well. So if you have a sphere and you draw two tangents from an external point, then these two tangents are also equal. We are not going to discuss the proof of this, but one quick easy way to understand is as follows. Every sphere can be seen as a circle from the side. So you can think of this as a sphere for that matter. And there is no reason why these two tangents can be unequal, or because the sphere can be seen as a circle. So I hope this can be used over here without proof. Alright, now let us see the proof of the theorem I just stated. The spheres touch the ellipse at the foci. Now of course the theorem assumes that we know that this plane is an ellipse. So anyway, we are not going to use the fact that it is an ellipse, but yes, this is something to be mentioned, that this plane is an ellipse, okay. Alright, now let's start with the proof. First of all, we can consider a circle where the sphere touches the sides of the cone. The locus of all the points where the sphere touches the sides of the cone, that locus is a circle. So here you see two circles because there are two spheres, okay. Now consider a point P1, a point P and a point P2 such that P1 lies on the circle, upper circle, P lies on the ellipse, rim of the ellipse, and P2 lies on the circle, lower circle. So these 2 points are collinear, okay. These are any random points which are collinear. Now please note that this P, point P lies on the ellipse, okay. This is a random point that lies on the ellipse. If I change P1 and P2, accordingly we can have a different P, okay. Anyway, so now due to the theorem number 2 over here, or the property number 2 which I just discussed, we can say that P, I will write here P f1 is equal to P1, because you see Pf1 is a tangent, because the elliptical plane is tangent to the sphere. So f1 is a point where the sphere touches the ellipse. We have not said yet that f1 is a focus. We are going to prove it. So f1 is some point on the ellipse where the sphere touches by definition, by construction, and Pf1 is a tangent therefore, and P1 is also a tangent by construction. So these two tangents are equal by property number 2, which we just discussed. Likewise, Pf2 is equal to Pp2. Again, property number 2, same argument. F2 is a point that the sphere touches the ellipse, and because it touches, it is a tangent, the ellipse is a tangent, and hence Pf2 is a tangent, and Pp2 is also a tangent by definition, and hence they both are equal by property number 2. Now if I add Pf1 and these two equations, if I add these two equations, then I get Pp1 plus Pp2, and Pp1 plus Pp2 is P1 P2, which is independent of P. It does not depend on P, and hence it can be said that it is a constant.